Hello, dynamic students. So, welcome to our first video on chapter 17. And this this chapter discusses rotational dynamics of rigid bodies in a plane. This first section, 17.1, will discuss moments of inertia, which should be review for most of you. This is a topic we covered in Physics 1. So the main objective for today will be to define and calculate moments of inertia for rigid bodies. And we're going to talk about the definition of things, and then something called the parallel axis theorem, and also how to find moments of inertia for composite bodies. And as usual, we'll do some examples and have a couple quizzes. The first reading quiz is as follows. So take a second and read it. The mass moment of inertia is a measure of the resistance of a body to, and the answer is C, angular acceleration. Moments of inertia are rotational quantities, not translational. And question 2, the mass moment of inertia is always negative, positive, integer, or zero about an axis perpendicular to the plane of motion. The best answer is B, it's positive quantity. All right, so over here, there's a machine with some big flywheel and whatever. And we want to understand how to calculate the moment of inertia for this flywheel, because that's going to be the number which governs how easy or hard it is to spin that flywheel. And the shape of and details of the flywheel will matter. Another example, we'll have a crank, and you got for an oil pump rig, and it's got rods and masses on the ends of rods, and you want to know how easy or hard it is to make the crank rotate. So the quantity which governs this for us is the moment of inertia. The moment of inertia measures how easy or hard it is to make something rotate. So we're talking about a problem here. So here's a kind of a generic lumpy body, and they're imagining you have some torque. It's nice that they use the proper term for it once. So torque, although usually your book calls it a moment. So we're going to have an axis Z, and then they mark out a little chunk of mass of size dm, and notice they define a perpendicular distance. And I say perpendicular, it's perpendicular to the axis of rotation, and they call that r. Okay, and from this kind of picture, they're going to come up with a number called I, capital I, the mass moment of inertia, and it measures the resistance of motion, or of rotation, about the z-axis, or the axis of rotation. All right, so let's talk about how do we define the moment of inertia about an axis, some arbitrary axis there. So I'm just going to have a little aside here. If I go over to the whiteboard space, in general, you should imagine we have an axis of rotation. Okay. And you should imagine you have a body, and it could be really could be irregular, it could be whatever you want. Okay. So we have an object, and what we want to do is study how this object can rotate about the axis of rotation. So, and it has to rotate rigidly. So, okay, the quantity which measures this for us is I. It's the moment of inertia. Now, and we're going to focus on rotations in a plane. So for us, it'll have a particularly simple form. In general, this is a complicated matrix of quantities. But in the special cases that we're talking about, we'll just have one number to compute. So the general relationship is that the moment is going to equal I alpha. That's what I want you to remember. We're going to come back to this in a little bit in more detail and specify the moment about what. And but that's roughly what we have in mind. Okay. So how do you compute this quantity I? It's going to be the important dictionary relating torques or moments to kinematic quantities like alpha. We need to know the definition of I. So I, for a point particle, so let's think about it here. So let's imagine I have an axis of rotation and I have a point particle of mass m. And what I would want to do is specify a radius from the axis of rotation. And I'm going to label that r perpendicular. That helps me personally to remember that I may or may not refer to the coordinate radius. I'm referring to the perpendicular distance. And then when I come up with coordinates, I may have to adjust my expressions a little bit. So the moment of inertia for a point mass equals m r perpendicular squared. Right. So that is the that's what you get there. Fine. Now, what if you had a more complicated shape? What if you had something? Whoa, what if you had something irregular? You know, like this. Well, as usual, when we want to, so we're going to study rotations about this axis. As usual, what we would do is kind of play Legos. So we would mark out and think about a little bit of mass, and each little bit of mass would have its own perpendicular distance, moment arm, you might say. And so the moment of inertia total for this continuous distribution is simply going to be the sum, which in this case will mean an integral, of the perpendicular distances squared integrated over all the pieces of mass. And implicit in this is that the moments of inertia for objects rotating about a common axis simply add. And that's what we did when we formed the integral. We found the moments of inertia for every little chunk and then added them up. And we'd be talking about moments of inertia about the same axis of rotation. Okay, so that's what we've implicitly done in this integral. It's clear because mass is positive and these distances, it's a distance squared, so that's going to be certainly a positive definite quantity. All right, so that's the general definition of moment of inertia. There's another, okay, so let's go back to the PowerPoint. All right, so, as far a comment on units. The units of moment inertia would be mass times distance squared. So in metric system, it's going to be kilogram meters squared. Or in imperial units, it would be slug feet squared. Or I suppose you could do it in pound mass feet squared, but your book works with slugs. So remember, hopefully we remember the relationship between slugs and pounds mass. Remember that one, let's do it over here. Remember, 1 lbf equals, well, we know that it's equal to 32.2 feet per second squared lbm, 1 pound mass, but it's also equal to 1 slug feet per second squared. Therefore, my unit ratio says that 1, the pure number 1, equals slug per lbm, sorry, per 32.2 lbm. Okay, so that gives us our unit conversion. If we were given a certain number of pounds weight, we know that, say, 10 pounds of weight is equivalent to 10 pounds, or is caused by 10 pounds of mass. And if you divided by 32.2, you'd get the number of slugs. So that's just a useful thing to remember in case you're out of practice. Okay, so some those results. All right, so here are some useful results that should be familiar from, sorry, I'm trying to erase the little markings. Here's some results that should be useful or familiar from Physics 1. The moment of inertia for a disk. So if you take that previous formula and you apply it to a disk of uniform density, we get the following result. The moment of inertia about the center, first of all, for a disk, which maybe is the most important one to know, is that it is 1/2 the mass times the radius squared. So the moment of inertia about this point is 1/2 the mass times the radius squared. The moment of inertia about this point here, kind of along the line of axis, along the x-axis, or along the y-axis, is actually 1/4 mr squared. And the moment of inertia, this is kind of an unusual one, about the axis parallel to the z-axis, but actually passing through the rim of the circle, or of the disk, is 3/2 mr squared. Other important ones, hopefully you remember from Physics 1, is that the moment of inertia about a rod, or sorry, a sheet of paper and a rod. So they don't really spell out a rod. Let me do that one here. Okay, so I'm going to let's go in here and okay, so the moment of inertia of a rod about its center. Okay, so if my axis of rotation was running through the center of the rod and it was rotating around the center, then that one would have a moment of inertia of 1/12 the mass times the total length of the rod squared. All right, and you can see that popping out of this rectangular example. If you look at this sheet and you imagine you rotate this about, say, the x-axis like that, then in fact it's going to be 1/12 the mass times the kind of the width in this case, because it's a 2D shape as opposed to just a rod, which is a 1D shape, but it'd be the width about perpendicular to that axis. And similarly for the y-axis, you get a similar kind of formula. Now, interestingly, about the z-axis, where you kind of are exposed to the entire area, it's actually the length squared times the width squared that appears, but again with the same 1/12 factor. And those are things that we derived in Physics 1, and we'll use those to build up more complicated shapes. All right, so when we have more complicated shapes, not surprisingly, we're going to have to do calculus. In this course, we're only going to look at shapes which are either surfaces of revolution or rotation or built out of such things. So to do that, you're going to have to remember how to use the methods of either shells or washers. And we'll have an example here where we go through that. Another very important result is the so-called parallel axis theorem. So the parallel axis theorem allows us to relate the moments of inertia about the center of mass to the moments of inertia about any other axis which is parallel to the original. So just a comment, when they write IG, that means the moment of inertia about the center of mass. Okay, so that's just a comment. So the book uses that notation throughout. So here's a situation where we have a body. This would have been maybe its moment of inertia about, about an axis passing through the center of mass, and then it has been slid over, and we're trying to find the moment of inertia about this new axis running parallel to the original. So it's been shifted by an amount d, and then that gives us simply that the moment of inertia about point axis A is the moment of inertia about the center of mass plus the total mass of the object multiplied by the perpendicular shift squared. Doing a couple examples that are useful just to know So let's insert a blank slide. Wow, let's use this one. So a useful result then would be, let's do a rod, for example. So we already saw, or I already claimed from physics 1, that the moment of inertia about the center of mass of this rod was 1/12 the mass times the length of the rod squared. Now, what if, on the other hand, we wanted to find the moment of inertia about this point? The mass is the same. Oh, I should have said this. This is about the center of mass, g. So here, the moment of inertia is now, that we want, is now about the end of the rod. So that has been shifted. So that's okay. The moment of inertia of this point for this rod about this axis would simply be the moment of inertia about the center of mass plus the mass times d squared. That was what the previous formula said. Well, d is the amount of shift, which in this case it's L over 2. So I would find that the moment of inertia would be, oh, this was supposed to be 1/12. 1/12 ml squared plus m L squared over 4. And then I do 1/12 plus a fourth. A fourth is 3/12. That gives me 4/12 is 1/3. So that's a handy little thing to remember. The moment of inertia of a rod rotated about its end is 1/3 ml squared. And that's generally how we use the parallel axis theorem, to go from knowledge about the moment of inertia around the center of the object to some other axis parallel to the original. Okay, so let's go back to our slideshow. All right, the following is just a definition. The radius of gyration, it's actually defined, it's k here. So, yeah, hope you're not getting dizzy, but I'm going to insert another slide here kind of explaining this. Okay, so you'll notice when you look at the moment of inertia that the units of I are kilograms, or it's really mass times length squared, but kilograms meters squared, which means that if you form the quantity, if you define K to be I divided by mass, and then take the square root, that's going to have units of meters. So it's going to be a length scale. It's called the radius of gyration. Okay, but what does that mean? Well, let's kind of unpack what this would mean. We're saying that the K squared times M equals I equals the integral of R perpendicular squared dm, which means you can actually think about K squared as, well, let's write it out. So that would be the integral of R perpendicular squared dm, and I'm going to divide by M total, the total mass, which is a constant. You might remember in Physics 1 how I mentioned that you could think about the distribution of mass in the object. And in fact, you can think about k squared as the average value of r perpendicular squared, where you weight by mass. So it measures, what it really measures is the spread of the mass about the axis of rotation. So when you have a large k squared value, then your mass is going to be distributed largely or widely around the axis, whereas if it's small, then it's a very tight concentration. And so this is a measure. So strictly speaking, k would be the square root of this quantity. K would be, you'd call it like an RMS value. Root means square value. It's analogous to, so maybe another way for those of you who took thermodynamics with me, K is analogous to the standard deviation of positions weighted according positions relative to the axis of rotation. So that's another way to think about it. It just measures the spread of the mass around the axis of rotation. Okay, we come to our first example. In the first example, it's some sort of weird cone-looking thing. It's symmetric though. We notice that it is a surface of revolution, and what they tell us is that this edge is given by the formula y squared equals x. The other thing we're told is that there's a density, a constant uniform density of 5 slugs per feet cubed. And the goal here is to find the moment of inertia for this body about the y-axis. Let's go through this. Why it just won't give me a blank one. Let's try this one. All right. So first comment. So let's draw the first thing. Let's get rid of this. All right. So let's draw the shape. I have this shape, and oh dear, I apologize. What they tell me is that this edge, they write the equation y squared equals x. That's supposed to give me the edge here. Well, that can't be right, first of all. So there's a problem. Y has units of feet, x has units of feet. So I have to multiply this by 1 foot, the constant, just to get the units right. So there must be a coefficient equal to 1 feet or 1 foot just to make the units work out. So to do this, what I would recommend, I mean, I suppose you can do, well, there are lots of ways to do this. I'm going to use a method of the washer method, or really I'm just going to think of this, build this shape up out of a stack of pancakes. So I'm going to imagine that I can make this shape out of a stack of pancakes like that. Okay, so, and they all have a common axis right down through the center. So if I can find a formula for the moment of inertia of one pancake or one disk, then I can add them up to get the full answer. So to remember, the moment of inertia for a disk is 1/2 m times the radius of the disk squared. Now in this case, if I look at my disk is going to have a radius which extends from 0 out to the maximum allowed value of x for a given height. So for me, that's going to become 1/2. Now the mass of my disk is going to be differential because it's going to be really thin. And then the radius is going to be x max, which is a function of y. I'm going to have to square that because that sets the radius of each disk. And okay, so in particular, I know that x max equals, as a function of y, equals y squared divided by 1 foot, just to get the units right. Okay, so that's easy enough. So I'm almost done. The only thing that remains is to sort out dm. And as usual, then I know that dm is going to be equal to rho times dv. And for a washer, or for a disk, I know that dv is simply the volume of that disk. So that's going to be pi times the radius of that disk. Well, that was x max squared times the thickness, which would be dy. Or plugging in, using my relationship between x max and dy, this becomes rho times pi times y to the 4th over foot squared dy. Okay, so now I know I have a formula for dm, I have a formula for x max. I can work out the moment of inertia. I is going to be the integral over y from 0 to 1 feet times, well, let's see, each one comes with a factor of 1/2. Each one comes with a factor of rho times pi. And then I'm going to have y to the, let's see, I get 4 factors of y from here, and I get 4 factors of y from dm, so that's y to the 8th. But I have to divide by 1 foot to the 4th, basically 2 unit conversions in x squared and 2 unit conversions coming from dm. And I think that's everything. Whew. So now I do that integral, and that's going to give me 1/2 rho times pi times y to the 9th over 9, and I have 1 over feet to the 4th. And then I evaluate that between 0 and 1 foot. So I get a final result of I equals rho over 18 times pi. And if you're keeping track of the factors of feet, I've got feet to the 9th divided by feet to the 4th times feet to the 5th. And then when I substitute in rho equals 5 slugs per feet cubed, this becomes 5 pi over 18, and you get slugs feet squared. All right, let's compare this to what the book had. Ta-da! All right, it's the same. They are a little sloppy there with units, and then just put them in at the end, and that's fine as long as you're on top of it. But anyways, I showed you how to work it out if you were not so confident. Let's do another example. Let's work out this situation. So here we have a pendulum made of a rod that has a mass, and then a disc. Okay, So the pendulum consists of a slender rod with a mass of 2 kilograms and a circular plate with a mass of 4 kilograms. We are to find the pendulum's radius of gyration about an axis perpendicular to the screen passing through point O. All right, so let's go through that. So we're after the radius of gyration, but that's going to involve all the other quantities. So let's insert a slide. I really just want a blank slide. So I'll do this, and then get rid of the title option there. Very good. Okay, so we have the following configuration. We have, we have a pendulum. It's hanging down from some point. There's a disc here, and we're told that this distance is 2 meters, and we're told that this distance is 1 meter, and we're told the mass of the rod is 2 kilograms, and we're told that the mass of the plate or disc is 4 kilograms. All right, and we want the radius of gyration, k. But k is defined to be I over m. And this is the radius of gyration about the pinned location, so about the point at the top. So if we label that point O, radius of gyration about point O. Okay, well, so this is a composite shape. So what we need to do is break it down into separate moments of inertia, one for the rod and one for the disc, about point O. So I want to say I total is I for the rod plus I for the disc. Now, okay, that's simple enough. So let me come up with formulas about that. Well, what I know about this is a rod, but we're not rotating it about the center of the rod. We're rotating about the end of the rod. Well, we already worked that out. The moment of inertia for the rod is simply going to be 1/3 the mass of the rod times the length of the rod squared. That was our previous result that we had where I showed you how the parallel axis theorem worked. It's almost like I knew where we were headed on this thing. Now I want to really do the same thing. I'm going to use the parallel. We've had the moment of inertia for a disk about the center of a disk, and then I want to shift it by the length of the rod plus 1 radius. So I want to say the moment of inertia of the disk equals the moment of inertia about the center of the disk. That would be 1/2 mass of the disk times the radius of the disk squared, plus the contribution coming from the parallel axis theorem. That's simply going to be the mass of the disk times, and how far have we moved it? Well, we've moved the disk down, so it would be 1 radius plus 2 meters. So that's going to be the length of the rod plus the radius. And I have to square that quantity. Okay, if you type in numbers, you get the following. You get that I for the rod is 2.667 kilogram meters squared. I for the disc is 25.5 kilogram meters squared. So the total moment of inertia equals 28.16 kilograms per meter squared. And since the total mass is 6, I can use that to find K equals 2.17 meters. Okay, let's see how we did. Good. This is the same. This is the same. This is the same. Looking good. They really proceeded just the same way we did. You get the same answer. So, good job. All right. I'm going to leave you here with a concept quiz, and then in class we'll have a group problem. So here's the concept quiz. The mass, moment of inertia of a rod of mass m and length L about a transverse axis located at its end is 1/12 mr squared, 1/3 ml squared, 1/6 ml squared, or just ml squared. And the mass, moment of inertia of a thin ring of mass about the z-axis, about the center here, right? This is, if you can see here, x is to the right, y is vertically upward, z is kind of into your eye. What would that be? Half mr squared, 1/4 mr squared, or 2 mr squared? So let's think about that. Just to see where we're going on the group problems if you want. First one we're going to do is a pendulum, and then we'll have another shape afterwards. So we're going to do 2 moments of inertia, where we'll have 2 group problems, but they're not too hard. Okay, I'll catch you next time.